have a very busy week ahead of us. Very busy week, right here. So, of course, we do the regular stuff, classes, recitations. That's the regular stuff, class recitation. Tomorrow and Thursday, you guys have a quiz. Tomorrow and Thursday, there is quiz number 2. Same deal, 6 problems, 30 minutes, 5 minutes each, just like the quiz 1. There will be office hours, mine office hours, there's office hours all the time, but my office hours on Wednesdays at evening, and there will be also office hours on Friday because the homework is due on Friday, homework 3. Then we have an exam next week on Wednesday. That is a week from tomorrow. Exam starts at 6:15 due to some scheduling constraints for some of you. Exam will start at 6:15. And we have 3 sessions. They're not quite scheduled yet, the time, exact timing, but they're 3 midterm reviews. Those are completely optional, voluntary. You don't have to show up. There's no points or grades for any of them. Those are held by the 3 instructors who teach the lectures. Okay? You can go to either one of them, or you can go to 2 of them. I don't think there is attendance. There's no participation, no grades, no papers. There's probably like 2 hours each. I will do it on Sunday. Professor Gold will do it on Monday evening, and Professor Aslam will do it on Tuesday. Professor Aslam is the one who wrote the book and has those class notes, book notes.
Where will we be able to find the locations and times?
Those will be announced on the website, but I think they're still trying to find the rooms. Figure out how many people can fit in those rooms. They open to all 600 students.
And same for the actual midterm?
The midterm is already booked, and every section has its own classroom time and so on and so forth. So on the website you should see that this section goes to some room at some time. There'll be the same exact paper like the other students, but at different rooms. Okay? I'm going to start now. Before I move on with our main material, which is counting. That's what we do right now, sets and counting. But before we do that, you guys are a little bit slow on proofs. Okay? So we looked at your proofs papers, and some of you did get an email or will get an email today from the TA saying, hey, you're not doing that good on proofs, which means you have to come see us, either me or the TA. Now, by that, I don't mean that you're going to get any points or coming in, but we are warning you that you're not fluent in doing proofs. Now, most of you have a good understanding of how stuff works, why stuff works, but how do you write it down as a mathematical proof? Just a warning, proofs will be in the quiz tomorrow and Thursday, and quiz will definitely be in the midterm next week. So especially if you want one of these people who did not submit the proof page, those 3 proofs, or who we get you an email saying you have to come see us, please be aware that you're going to have to do proofs this week. And I think proofs are also in the homework 3. All right? So, before I move on, I want to give you 5 proofs right now. Okay? But I'm not going to finish them. I'm going to start each one of those 5 proofs, and you have to finish them by the quiz, aka by tomorrow. Now, they shouldn't take more than 15 minutes to finish at home. So when you go home tonight, look at those 5 proofs and say, okay, what's wrong with this guy? What he did in class? Let me finish those proofs, okay? Just as an exercise. Because we looked at those papers yesterday with the TAs, and I think we have some deficiencies on proofs. Now, the proofs don't have to be complicated things. It doesn't mean what I'm going to do after those proofs in the lecture today is going to be much more complicated than the proofs. Nevertheless, the question is, how do you write properly a proof? So, problem number 1, which was from recitation. I have some f function that takes reminders into reminders. That was the 3rd proof in that page, right? For example, maybe f of x is 2x mod n. Or maybe f of x is x plus 5 mod n. Or maybe f of x is x cubed mod n. Any one of these functions will take a reminder and produce another reminder, mod n, right? Proof that applying f repeatedly values start repeating. That was the question. I think there was a specific function given in that proof. I think it was like a times x. Doesn't matter which function it is. So how do we do a proof here? The proof we're going to put in parentheses, it's based on, it's a good idea to tell what you're basing on proof on, what kind of mechanism it is, informally. Pigeonhole principle. It's not required, but it's a good way to tell the reader, hey, I'm going to apply that principle now. So here's what we're saying. The sequence of repeated f applications is, you start with the value x, the next one is f of x, the next one is f of x, the next one is f of x, so on and so forth, right? Because that's what it means to apply repeatedly f. I apply it to some value x, I get the result. But that result, I can apply f again to it. And that result, I can apply f again to it, and so on and so forth. The sequence, this, is infinite. Right? I can apply f until the time ends. But all values are in Zn, which is finite. Zn only have n values. So the pigeonhole principle says if you put too many things in too fewer boxes, things are going to start fitting in the same box, right? In this case, we have a huge amount of things, infinite, into a limited amount of boxes. So from that principle, some elements in the sequence are the same value or repeating. That's it. That's the proof. The issue is the sequence is more than the boxes I have or the values I have. Therefore, some of these elements in the sequence, I don't know which ones, are going to have the same value. So as an example, that's not part of the proof. If f of x is 2x, then f of x is f of 2x, which is 4x. F of x is f of 4x, which is 8x. That's all modulo m. And f in general, f of f, k times applied to x, it's going to be 2 to the k x mod n. Because every time I apply, I multiply by 2. If I applied k times, means multiplying by 2 to the k. 2 times 2 times 2 times 2. That's what this function does. Every time it gets applied, it multiplies by 2. So repeating in this case, means that 2 at kx it's the same as some 2 as hx for some k bigger than h. It means at some point these values start repeating. Yes?
So we're not saying that they definitely all values start like stable and repeating. We're just saying that some values are the same as.
Right, but we can further prove for certain functions that once they start repeating, if this value here is the same one here, it's easy to see how after that, the next value is going to be the next value, right? If this value is some value A, and this is some value B, sorry, this is also A. The next value is going to be f of A, and the next value here is going to also be f of A. So once they start repeating, because they both apply f to the previous values, those values are the same, the next values are going to be the same, right? So while that's not claimed, we're not claiming any cycle or anything like that, because f is a function, it's going to force starts to start repeating in a cycle. Now, that's true for any function, not just 2x. X plus 5 will have the same property. Once it starts repeating, it's going to start cycling. And any other function. So that's one. How about another one? This I really didn't leave you anything to do with this one. This I've done, the whole thing. So, proof number 2. A, B are integers such that 3a plus 2b equal 28. Prove that 5 does not divide the GCD of AB. So in other words, any two integers that satisfies that property, 5 cannot be a divider of their GCD. How would that proof go? Actually, let's do two things. It's part A and part B. 2 divides the GCD of AB. So I want to prove two things. That the GCD divides by 2, but the GCD does not divide by 5. Okay? So how would I start this proof? This thing, I always start with the GCD. Informally, I'm just going to say GCD is a value. I'm not going to say GCD of AB. It's that GCD of AB. So let's say GCD is the GCD of AB. GCD divides A, that implies GCD divides 3a. GCD divides b, that implies GCD divides 2b. So of course, that's what we've done on GCD. It's going to divide 3a plus 2b. In fact, GCD is going to divide any linear combination of a and b. It doesn't matter 3a and 2b much. Any way you pick two coefficients, 3 and 2 in this case, what you get is a multiple of the GCD. Because GCD divides A, divides B, it's going to divide any linear combination of them. Like, for example, minus 5A plus 17B. Because both A and B's are multiples of GCD, their linear combination is also a multiple. So now that means GCD divides 28, right? Because 3A plus 2B is 28. That's what the premise is telling me. Now, from here, you should finish the proof for part A. Why, if the GCD divides 28, 5 cannot be a factor of it. Well, for part B, I'm going to say 2 divides 2b, and 2 divides 28. That means 2 divides 28 minus 2b, right? 2 divides this, it has to divide the difference. So 2 divides 3a. Because it divides this quantity and this quantity, it must divide the difference, which is 3a. So from here, you're going to finish part B at home. Why is it that if 2 divides 3a, then I have stuff going on? Okay? Problem 3. N is the number integer that is 1 modulo 2, and x is n minus 1 by 2. Please observe this is an integer, because if n is 1 modulo 2, if I subtract 1 and divide by 2, I get an integer, because n minus 1 will be even, divided by 2 is an integer. Prove that x and 4x are inverses to each other modulo n. So that's the problem, that's the solution. What we want is to show x, 4x inverses, or actually let's write it better, 4x is the x of minus 1 modulo n. That's the same as saying we want 4x times x to be 1 modulo n, which is the same as saying 4x squared to be 1 modulo n. That's what we want, which is the same as saying 2x squared to be 1 modulo n. Again, the problems ask us to show that those two numbers, which are integers, are inverses to each other mod n. So we just took the conclusion and say, what does it mean to be inverses? It means when I'm multiplying, I have to get 1. And then what does that mean? Well, 4x times x, it's 4x squared, which is 2x everything squared. And now I have to figure out from here who 2x is. So, but who's 2x? N minus 1 by 2 is x. That means 2x is what? You guys can finish this up. Problem 4. If P, Q, R are prime numbers and F is their product, then P of n is P minus 1 times Q minus 1 times R minus 1. That is the problem. That if a number is a product of 3 primes, then phi of n, the number of coprimes with it, has this form. That's part of your general formula, right? It's like what you had in homework 2. There was a formula that if you do it in this particular case, you get exactly this expression. How do we prove such a thing? Yes?
The inclusion, exclusion principle.
Very good. So how do we prove this? We say, who is the set of coprimes? Phi of n is the size of the set of coprimes with n, right? But who is this set? This is, so the set of coprimes remainders with n. So we can write this as all remainders minus the non-coprimes. The Con is a set of coprime remainders, but that's the same as saying it's all remainders minus the ones that are not coprime with n. So this is who? This is all remainders minus, who are the non-coprimes with n? it's the numbers x in Zn that have the GCD of x and n not 1. Because if they're 1, they're coprimes. So we're looking for the non-coprimes. That is the ones that have non-zero GCD. That is Zn minus the multiples of, how can I get a common factor with n if n is p times q times r? The common factor must be p or q or r because there are no other factors. So those are multiples of p or q or r. This non-coprime set that I want to take out is the multiple of either p or q or r, which is the multiple. I'm going to state MA means multiples of A is MP, sorry, multiples of P, multiples of Q, multiples of R, let's say in Zn. So this is a union, is the union of multiples of P or Q or R, means union. But I have a formula for this size, right? So now I'm saying the size of this formula, MP union MQ union MR, I apply the inclusion-exclusion principle to get the size of MP plus the size of MQ plus the size of MR minus the size of, who is the MP intersect with MQ? What are the multiples that are intersect? I say the multiples MP intersect with MQ, the ones that are multiple of P and of Q, is in fact the multiples of PQ. That's something you can prove at home. That if you want something to be a multiple of P and Q to be in the intersection, that has to be a multiple of the product, PQ. So that's the same set, minus PR minus QR plus MPQR, which is MP intersect MQ intersect MR. That's the same set. To be a multiple of P, Q, and R, you have the multiple of P, Q, R. So now, how many multiples of P are there? That's something you have to prove at home. How many multiples of P are in the remainder set? The answer is QR multiples. Why is that? That's something you have to prove at home. How many multiples of Q are there? PR. How many multiples of R? PQ. How many multiples of PQ? R. How many multiples of PR? Q. How many multiples of QR? P. How many multiples of PQ and R? There's only one remainder that's a multiple of P, Q, and R, which is what? What remainder in the end is a multiple of all three? That's the same as P times Q times R is N. What remainder is a multiple of N? Yes? 0. So that's one guy. Now, I've just computed the size of this set, but looking at this, I really want the phi of n. Now, the phi of n is the size of the difference. How many remainders are there? PQR, that's the size of Zn, minus this whole thing. So it's minus QR, minus PR, minus PQ, plus R, plus Q, plus P, minus 1. And this should be P minus 1 times Q minus 1 times R minus 1. Is that true? P minus 1, Q minus 1, R minus 1 is this whole expression here?
What is the number of multiples of P equal to QR?
That's something you have to prove at home. You count them. They start from 0. The next multiple of P is what? P, 2P, 3P, until you see which one's the last one. That creates an index. And then you count the index, should be QR of them. let's check quickly mentally this expression. If I open parentheses, P times Q times R, it's PQR. P times Q times minus 1 is minus PQ. Q times minus 1 gives me what? For example, Q times minus 1 times minus 1. That will be plus Q, somewhere in here. Minus 1 times minus 1 times minus 1 gives me minus 1 times minus 1 times minus 1 gives me minus 1. Right? So when I open 2 times 2 times 2 parentheses, how many terms should I expect? There's 2, 2, 2. How many terms do I expect? 8. How many terms do I have here? 1, 2, 3, 4, 5, 6, 7, 8. You should open this parenthesis, make sure that works out. Okay. So I left some things that are a little bit ambiguous, why that is. Why is the number of multiple QR? Why is the size and so on and so forth. But the schema of the proof is here. That was number 4. Number 5. So one of these proofs could be in the quiz, and another one in the midterm, or something very similar to this. And this is kind of what I'm expecting you to write informally, but the flow of thinking has to be there. Last one, number 5. P of A is the set of subsets of A. Say A has n elements. Now we want to split this P of A into 2 categories. These are all subsets with k elements, and these are all the subsets with n minus k elements. Say, for example, this works in general, but just to make it clear, n might have 5 elements and let's say 7, and k might be 3. So this is all the subsets that have exactly 3 elements. If A is 1, 2, 3, 4, 5, 6, 7, sub-element sets in here might be the sets 1, 3, and 6. That's a set with 3 elements. So is in this set. So those are B, those are other things. And elements in here might be 2, 4, 5, and 6, because it has n minus k would be, of course, 4. What this problem is asking, show means proof. Show that this, I'm going to call this the set X and Y. X and Y have the same size, which is the same as saying the number of subsets with k elements is the same as the number of subsets with n minus k elements. So the options in here again for 3 element set are things like 2, 5, 7, so on and so forth. And here are all the subsets with 4 elements like 1, 2, 3, 4, or 1, 3, 5, 7, so on and so forth. What it's saying, show that if you count those sets of 3 elements and you count those sets of 4 elements, you get the same number. Now, these are not all the subsets of P of A. These big subsets X and Y are all the subsets with 3 elements, all the subsets with 4 elements. Are there any other subsets in P of A? Like, for example, who? Subsets of 1 element, or subsets of 5 elements, or of 7 elements, or the empty set. P of A contains more elements than the ones in X and Y. Right? It contains other stuff. But we're not worried about that stuff. The problem is saying, we show that those two sets are equal sizes. How do we show that? Yes?
You could use combinations in the formula for combinations.
I can use combinations. I say, I know how many sets of size k are there. How many are there?
The n choose k,
N choose k. And how many elements are there?
n choose n minus k.
N choose n minus k. Are those the same value? N choose k and n choose n minus k. Well, I could figure out that factorial formula, right? Remember that formula? We're going to talk about it in 5 minutes. If you open up this is the formula for k, but if you apply it to n minus k, you get the same denominators. N minus k is here, and n, this is n factorial n minus k, and the other one is n minus k factorial, but that is just k. N minus k is k, so I end up with the same thing. So that's proof number 1. I have a proof number 2 here that you have to finish at home. I'm going to construct a function h from x to y. Function h takes a set from here, produces a set in here. Guess what this function is? It takes a set h. What is the set that's being produced? Takes a set to 3 elements. I want to produce a set of 4 elements. And I want this h to be a bijection, a one-to-one mapping. Yes.
Okay, h of x equals to h of y.
H of, sorry, that's a v. So v is in x. So I take a subset with 3 elements like 1, 3, 6. What subset should I produce? Yes.
Let's just do the complement.
Complement to respect to a,
Yeah.
right? Because a is the whole thing. It's a minus v. So it takes a set, any set of 3 elements, and produces its complement. So who's the complement of 2, 5, 7? 1, 3, 4, and 6. Who's the complement of 1, 3, 6? Complement of 1, 3, 6, if I take a minus that, I get what? 2, 4, 5, 7, right? Now, what you have to prove is this function is a bijection. That means it's a one-to-one pairing. Everybody in this set has a corresponding in this set. Every subset of 3 has a corresponding complement of 4, and every set of 4 has a complement of 3. And remember what I tell last time? If a function is a bijection between 2 sets, x and y, they must have the same size. Every one-to-one pairing between 2 sets implies the set of x has to be the same as y. But why is h a bijection? That's something that needs to be shown. Somebody pointed out after the last lecture, who pointed that out? Maybe he's not here today. That bijection and one-to-one might mean different things in different parts of the world. I say one-to-one means bijection, but in some cases one-to-one it's only injection, which is one of the 2 bijection properties. So to be clear, whether you call it bijection or one-to-one, what we really mean is that there is a pairing between these sets and these sets. And everybody here is paired with somebody here, everybody's here is paired with somebody here. In mathematics, that's called a bijection, which is both injective and surjective. Now, sometimes one-to-one means only injective, sometimes means bijective. Be clear what you mean. So those are my 5 things for you to look at. And if you have questions about the proofs, we looked at the other proofs, the first 2 proofs that seems to be more or less okay. The first one, the repeated f, about half of you didn't do it. Proofs are going to happen tomorrow, Thursday, and in the midterm. With that, we need to move on. So where are we? We are at combinations and permutations. So what are combinations? Actually, let's start with permutations. It's so-called P of n ways to permute n elements, or to arrange if you don't like permute. For example, if n is 5 and the objects are A, B, C, D, E, then the permutations are 5 factorial, that is 5 times 4 times 3 times 2 times 1, and the arrangements are A, B, C, D, E, A, B, C, E, D, A, B, D, E, C, A, B, D, C, E, so on and so forth. I think everybody understands why this is 5 factorial. This is the possibilities for first. There's 5 options for the first things. Then once I pick the first, there's 4 possibilities for the second, 3 possibilities for third, and so on and so forth. That's what we get in 5 times 4 times 3 times 2 times 1. Because if you want to arrange them, the order matters here. The order matters. Otherwise, if the order wouldn't matter, those things would be the same exact thing. But they're not. There's 5 factorial ways to arrange them. Now, what is combinations? Ways to select a set of K out of N. So order doesn't matter. It's a subset, okay? So if I have this set, possibilities are to select the sets. For suppose K is 3, I can get A, B, and C. That's a set of 3. Or I can get B, E, and D. Or I could get A, C, and D, so on and so forth. So when I choose a subset of K out of N, that's out of order. So this order doesn't matter, and that order matters. For example, do a quick example here. Example. I have 10 packages which are 6 heavy plus 4 light. If I want the number of ways, when I put this DS sign, means number of sets, ways, people, students, houses, number of ways when I put this DS sign. Number of ways to select a subset of 5 packages. That is 10 choose 5. This number here is called n choose k. How many ways can I select a subset of k out of n, out of order? So if I want 5 packages out of 10, that should be 10 choose 5, because I have 10 packages and I can choose 5 of them. But what if I want the number of ways to select a subset of 6 packages, but they have a property. I want 3 heavy plus 3 light. So I really want 6 packages, 3 being heavy, 3 being light. How many ways I have to do that? In how many ways can I select 3 heavy packages? 6 choose 3 for the heavy. And in how many ways can I select 3 light packages? 4 choose 3, that's the light one. And what do I do now in between? Do I add them up, subtract them, multiply them? What do I do with those two numbers? What do I do? So that's the number of ways to get 3 heavy packages. There's a number of ways to get 3 light packages. How many ways to marry them up? To create a combination of 6 packages. Anybody? Multiply. This is like number of pants, and this is like the number of shirts, right? Pants times shirts. Every 3 packages here, every pants is 3 packages, heavy ones. With any shirt, that's 3 packages, light ones, creates a unique combination, right? So that's why they get multiplied. Is this number of independent possibilities, also called product rule. Did I count everything? Is what I have here is all the possibilities to create 3 heavy and 3 light packages. Did I miss anything? No. That's the first question on counting. What's the second question? Did I count anything twice? Is there any combination of 3 and 3, heavy and light, that somehow I miscounted because I counted more than once? No. So always ask those 2 questions. Did I count everything? Did I miss some possibility? And did I count anything twice?
What's the formula for n choose k? Yeah.
We'll get there in a second.
Okay.
There's a formula written somewhere on the board. But we would like to think of n choose k not in terms of factorials, but rather in terms of how many ways to choose a subset of k out of n. Yes?
If order doesn't matter, why are there different ways to arrange heavy boxes if they're always just a few boxes?
The order doesn't matter. It's 3 heavy and 3 light. There is no order. But the packages are different. They're not the same package.
Oh.
It's package A, package B, C, D. So let's say the heavy packages are A, B, C, D, E, and F. That's the heavy packages. And the light packages are 1, 2, 3, 4. Order doesn't matter, but which packages you pick matters. So a possible combinations would be to pick A, B, C out of order. We're talking about the set A, B, C combined with the set 2, 3, 4. That will give me what set? A, B, C, 2, 3, 4. Or I could have picked B, E, F and the set 1, 3, 4. That will be now a different possibility. Every way I can choose 3 in here and 3 in here, I get a new set altogether. How many people follow me? Hands up. Good. Now, what is n choose k numerically? N choose k is the number of picking k out of n, or a subset of k out of n. But how do we compute that? So here's what we said last thing on Friday. We said, look at the permutation. These are n elements here. And we're going to chop this at k and n minus k. So how do we compute n choose k? We're going to look at all permutations of n. So we do all permutations of n. That is n factorial. We know that from here. If you try to arrange n elements, you get n factorial possibilities. And then we pick the k is the prefix, and n minus k is the suffix of that permutation. For each permutation, I say this permutation generates a set of k and a set of n minus k. The problem with this is that each permutation generates not a set but a sequence. Permutations are in order, so those k will be in order. Those n minus k will be in order. So this is in order. This is also in order, the suffix, right? Because again, when I put here a permutation, I get it in order. Now, if I am to chop this as a set, so make out of this a set of k, and out of this a set of n minus k. I'm going to get the same arrangement of sets many, many times. So, for example, suppose this is the elements A, B, C, D, E, F. What did I have there? 6, and that's 6, and that's 4. 1, 2, 3, 4. These are the elements in here. As a sequence, this is a permutation of 10 elements. As a sequence, this is an exact sequence of 6, this is exact sequence of 4. But then if I am to move it into a set, which is A, B, C, D, E, F, and then the set 1, 2, 3, 4, this is the prefix, this is the suffix. The same set, the same two sets, are obtained many, many times. For example, another permutation, B, C, D, A, F, E, and 3, 2, 4, 1, produces the same exact result as sets, not as sequences. If I look at it as a sequence, I get a different sequence. But if I look at it as a set, I get the same set. Right? So now, all the permutations are 10 factorial. How many of these permutations produce the same exact two sets? Here's one that does not produce the same. So those are the same, and those are the same as B, A, D, C, E, F versus 1, 2, 4, 3. They produce the same two sets. Anyone, those are different permutations of 10 objects. They're always going to produce those two sets. How many ways are here to produce these exact two sets? How many permutations of the 10 factorial produce exactly this set as a prefix and this as a suffix? So how many ways are here to arrange 6 elements? This is 6 factorial. And how many ways are here to arrange those 4? 4 factorial. And is this a product rule? Any way to arrange these times any ways to arrange that gives me a new permutation of the 10? Yes. Did I count all possibilities to obtain this set and that set? Did I miss some permutation that will produce these exact two sets? No, because anything obtainable from this set is a permutation of the letters versus a permutation of the numbers. So the number of permutations that produce these exact two sets are 6 factorial times 4 factorial. Here's a permutation that does not produce that set. A, B, 1, 2, C, F versus D, 3, E, 4. That is one of the 10 factorial permutations, right? But what are the sets produced here? A, B, 1, 2, C, F versus D, 3, E, 4. What is another permutation of all 10 that produces exactly those two sets? 1A, C, F, 2B versus E, 4, 3D. This permutation produces the same exact two sets. Now, how many ways I have here to produce these particular two sets? 6 factorial times 4 factorial. Because there's 6 factorial ways to permute the first set, and there's 4 factorial ways to produce the second set, and any concatenation of a permutation here gives a permutation of the all 10 of them. So what this is telling us is that every particular arrangement of 6 versus 4, any n choose k, because choosing k is the same as choosing n minus k, right? By choosing k elements, the remaining are n minus k. That was the bijection I just showed 5 minutes ago, that if you choose n minus k is the same as choosing k same as choosing n minus k. That's how you either want the ones that are remaining in the pot or the ones that you take out. But the selection is effectively the same thing. But any one of these sets have been produced k factorial times n minus k factorial. So if I want the number of different ways to produce sets, which is n choose k refers to how many arrangements of selecting k and remaining with n minus k. How many different sets are there? This is one way, this is another way, and this is another way. E, 2, 3, 4, F, C, B, let's go next, versus A, 1, B, D. That's another way to select 6 versus 4. This is only 6 versus 4. 6 versus 4. And how many ways, how many permutations give me exactly this 6 versus 4? 6 factorial times 4 factorial, because there's 6 factorial ways to permute those and 4 factorial ways to permute those in here. Any way of the n choose k way to select 6 is being produced in 6 factorial ways times 4 factorial ways. So the number in here is going to be the total number of permutations, but each result as a set has been produced that many times, so I have to divide by how many times I'm counting each element. Again, how do I produce this? I look at all n factorial sequences. I chop it at 6 versus 4, k versus n minus k, and I say, look at it as sets. There's a set produced and another set produced. Now, each way of splitting into k versus n minus k has been produced repeatedly, k factorial times n minus k factorial times. So now if I want to count each selection once, I have to divide the number of total results by how many times each of them is repeated, right? If I count 3 students, each of them 5 times, I get 15 counts. So divided 15 by how many times I counted each item, that is that many times, I get the number of different items. In my example here, the number of selecting k out of them. That is n choose k. So we need to do 2 things here. So n choose k, sometimes it's called C of n and k. So if you see C of n and k, don't be scared, it means the same as this. Most people in Europe use this. In here, I think it's mixed. I would encourage you to use this sign, but if you prefer this one, that's fine. So if you see C and k, that's the combinations. P of n is the permutations. And there is an additional one, which is really an application of those 2, which is, I want to do the same. It's called k permutations. But the name doesn't matter. The notation is nk. What this does, it says, I want to, in English, select a sequence of k. So the difference between this and the combinations is this one saying select a set of k. That one saying select a sequence of k. So I'm going to do the same. I'm going to look at all the n factorial permutations, chop it off here. But when I chop it off, say I'm A, B, 1, 2, C, F at 6 versus 4, D, 3, E, 4, because I want to produce a sequence now, not a set, I'm going to say the result is the sequence A, B, 1, 2, C, F, because that's what I want. I want the sequence K is 6 in this example. And the remaining part doesn't interest me, that's still a set. Right? So this K permutation says you have n objects, you put them in all n factorial permutations, you chop K of them, K equals 6. This remains a sequence. Order matters. But the ones that are remaining, that you're not selecting, it's a set. You don't care in what order those ones are remaining on the table. Right? So again, the ones that we select are a sequence. Now, in how many ways can I obtain this result? How many of the n factorial permutations will give me exactly this sequence and the remaining set of 4?
N minus k factorial. So in this case, 4 factorial.
So I can obtain the same from another permutation, which is A, B, 1, 2, C, F, but in here I get 3, E, 4, D. Right? Any permutation of the remaining objects will give the same exact sequence. The sequence is what I want to take out of here. Right? So how many permutations will give me this? It's n minus k factorial ways, because now I can only permute the tail. I can only permute the ones remaining on the table. These ones are not permutable, because as soon as I permute them, I get a new sequence. In here it was okay to permute those, because every time I permute them, I get the same set. But in here, since I want the sequence, as soon as I move those around a little bit, they're not the same result. Who's with me on this? Okay, this is something you guys are going to need to sleep on. After the quiz, we're going to make sure we understand how this works. So there are more, of course, more ways to obtain sequences, because sequences are in order, sets are out of order. And now if I do the same calculation, P of nk, it's going to be what? N factorial. That's all the permutations I had for n objects. But now each particular result, like A, B, 1, 2, CF, has been counted how many times? This many times. Right? In here, I had to divide by ways to permute this, because every way to permute it will give me the same result. In here, I don't count those ways, because every way to permute them, it's a different result. So, by the way, I could have thought of this in a different way. Instead of thinking about it that way, which is perfectly valid, I could have thought that's n choose k times k factorial. Why is that? Why this P of nk? Instead of thinking about it this way, I could have thought, what is this way? Run on all n factorial permutations, and then count how many times the tail was the same set. So divide by that number to get the unique counts of sequences of 6. Where can I get this result instead? What's the thinking that will give me n choose k times k factorial? So that is n choose k times permutations of k. Yes?
It's like you get the number of combinations and then
I get the set of k first
and then you permute it.
in all possible ways.
Yeah.
Which is k factorial. So I could have thought of these sequences by saying, choose the k elements that you want in your sequence first. How many ways to choose k do I have? N choose k, right? And then, since I want a sequence, there's k factorial ways to permute those k objects to get the sequence out of them. And it's no surprise, like numerically, why is this true? Why n choose k times k factorial will give me exactly this. Because n choose k is this divided by k factorial. So when I multiply with k factorial, I get back this thing, right? Are we following this? N choose k, it's kind of this fraction, but it has a k factorial denominator. So when I multiply with k factorial, I get back this. So this, you're gonna see it in the homework and assignments, k permutation. That is, choose a set of k and then permute it in all possible ways. Another example that's important here. So you should think of these as big objects, 1 and 2, big definitions. And this here is more like an application. This is just a way to use permutations and combinations to give you this stuff, which is how many ways to select a sequence of k, not a set of k. Here's another one application that is important. I have now 4. It's called balls into bins. Also application. And these are nothing else, just ways of counting things. But those are fundamental definitions, ways to permute things, ways to select the subsets, while these are just derivations out of them. I have n balls and oranges, which are the same. How many ways to distribute k students? So what I mean by the same, oranges don't have IDs. There's no orange 1 and orange 2 and orange 3. They're just a bunch of oranges. So the only thing that matters is the count. And how many ways can I take 100 oranges and split into like 20 kids? Kids are the bins and oranges are the balls. I could have done this with sheets of papers distributed to people who write stuff, right? I have 500 sheets of paper. I have to distribute them to like 20 writers. Now, sheets don't have IDs. There's no sheet 1, sheet 2, sheet 3 of papers. It's just how many you get. It's just a count. So how do I think of that? In how many ways can I distribute a bunch of identical objects? Same means identical objects. Or no IDs. See, every time I say A, B, C, D, E, my object have IDs in here. This object D, it's obviously not the same as object A. That's why it's called D. So you can tell it's different than A. Object 2 is different than object C, so on and so forth. These objects have IDs. Oranges or balls or sheets of papers do not have IDs. They just are like a sea of the same thing. But they have counts. I can say how many oranges or how many balls or how many sheets of papers do something. So in these kind of problems, we treat all objects the same. There is no choosing a set. There's only one set of k, which is a count of k. You can't choose different subsets of k because you need IDs to choose different subsets. How many ways can I do that? How do I count this? I need a new mechanism here. Just like I invented a mechanism here, how do I look at my oranges? Yes?
So I think you could do like, if you draw n oranges or like n circles.
Let's do that. So I draw the n oranges, here they are. Right?
Yeah.
And then what?
So you want to distribute it to k students. So basically you need to like break those n oranges up into k.
So let's say k equal 3. A possible split would be, here's a kid that gets those 2.
Yeah.
Here's another kid that gets
I guess
those 5, and another kid that gets those 3, right?
Right.
So it comes down into how can I distribute them into 3 buckets or kids or rooms? Yes.
Can a student get 0 or no?
Yes.
Yes.
So a bin, what I say here, bins, a bin can be empty. Seems unfair that the kid gets no oranges, but it's a possibility. So how do we count this number of ways? So here's how we're going to do it. Oranges or balls are fixed as a writing sequence. Because they don't have IDs, there's only one way to arrange n oranges, which is one after the other. Permuting those 2 oranges doesn't do anything because there are no IDs. They'll be the same exact arrangement. There are k-1 separators between bins. If I have k bins, notice that I have k equal 3. How many separators between bins I have? 2 of them, right? Yes.
Could you have like also k minus 2 separators then?
No, because I need to split it into 3.
Like if a student has 0.
If a student will be 0, that will be 2 separators one after the other, indicating the 0 in between them, right? That means a kid gets 7 oranges, a kid gets 0 oranges, and another kid gets 3 oranges, right? But there's still 2 separators. So how many total symbols? If I have n oranges and k-1 separators, how many things I draw on this line? N plus k-1. And what is my choice effectively here? What is my choice? What are my possibilities for me in writing this up? Oranges are always rounds. They all 10 after the other. Separators are always bars. This changing the separator between them, moving this bar here and this bar here, doesn't change anything. So what is my only choice in creating a new partition of oranges to the bins? What can I choose? What makes this different? What makes this different? Where the bars are. Right? Moving this bar from here to here creates another separation into bins, a different one. Right? So effectively, how many positions I have here? N plus k-1. And my choice is effective, choose the spots of the bars. Right? That's what it comes down to. Write so many symbols, n plus k-1. In this case, that would be if n is 10, k is 3, n plus k-1 will be 12. So I have 12 objects, and the choice is choose k-1 separator positions. Are those positions for the separators a set or a sequence? So let's count this, let's count the spots. This is spot 1, 2, 3. Separator is 4, 5, 6, 7, 8. Another separator is 9, 10, 11, 12. I have 12 spots, right? Choosing the separators is choosing a sequence or a set? Am I choosing positions 4 and 9? Or am I choosing the sequence 4 and 9? If I choose 9 and 4, is the same as if I choose 4 and 9? Does the order matter? No. So what am I choosing? A set of k-1 out of how many symbols are total there?
12.
n plus k-1. So how many ways to choose the separator positions are there? N plus k-1, total number of objects. Oranges plus separators. This is balls. plus separators, and I get to choose k minus 1 separators positions. It's a set, so it's n choose k, because I'm not choosing 4, 9 as a sequence. 9, 4 will be the same. But what if I choose the separator, so that's 4, 9. What if I choose the separators to be, for example, 3 and 5? How would that look like if the separators are in positions 3, 5? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Separators are in position 3 and 5. So here's a separator, here's another separator. Balls or oranges are in the other positions. So the distributions of oranges into balls is 2 in the first bin, 1 in the second bin, and the remaining 1 in the third bin. Now, in all this question, in all this mechanism of doing this, I hope you guys follow me what I did here. It comes down to choosing separators among the oranges. The oranges have no IDs. There's no point moving the oranges to each other. How about the beans? Do the beans or the kids have IDs in here? If this is the first kid gets 2 oranges, the second kid gets 1 orange, the third kid gets 7 oranges. What if the first kid would get 7 oranges? Would that be the same or different?
Students are different. Yeah.
The way I thought about it, would the separators be in the same position if the first kid gets 7? Where would be the first separator to get to the first kid 7 oranges? In the position 8. Is that the same choice? No. So beans have IDs. That is, there is a bin 1, bin 2, bin 3. That's bin 1, bin 2, bin 3. Ask yourself these kind of questions. When I split students into classrooms, do students have IDs? Is student 1 the same as student 2, the same as student 3, or they're different entities? Do classrooms have IDs? Is the classroom 1 same as classroom 2, same as classroom 3, or they're the same? Right? So this is a way to think about things as an exercise for counting. Let me see if I have an example here. I'm sure I do. Example of balls into bins. I have in this class there are 600 students. That's 600 birthdays and 365 days, which are day 1, day 2, up to day 365. How many ways to distribute birthdays into calendar days? Do birthdays have IDs in this question as a distribution? Birthday, I should say birthday counts. Like, I don't care about whose birthday it is. I'm just counting how many birthdays are today. When I say that, are all the birthdays the same or they're different? Do they have IDs? So that's the first thing you should ask yourself. It's asking me to distribute, here's are the days, day 1, day 2, day 3, all the way to day 365. When I put a count, I say just January 1st, right? January 1st, January 2nd, this is December 31st. When I put a count here, I say 5 people are born January 1st. Did I imply the students have IDs or not? No. I'm only counting the birthdays. Doesn't matter which 5 are there. I'm just saying there are 5 in there. So that's the oranges now that have no IDs, because they don't matter which one orange is it, just the count matters. How about the dates? Do the dates have IDs here?
Yes.
Is January 1st the same as January 2nd? No. So how many ways to distribute 600 birthdays into 365 bins or days? Is that the answer? Are we in exactly the situation where we distribute identical oranges into buckets or bins or days or classrooms that have IDs? So that would be what? 600 plus 365 minus 1 chose 365 minus 1. Which of course, because n choose k is the same as n choose n minus k, that will be the same as 600 plus 365 minus 1 choose how many? You can think of this process, instead of picking the separator positions, pick the oranges positions, because what's left, it's the separators, right? If I have to choose what positions are oranges and what positions are separators, picking the separators position for 9 is the same as picking oranges in positions 1, 2, 3, 5, 6, 7, 8, 10, 11, 12. Because the remaining positions will be the separators. How many people follow this? I think balls and beans are a new thing for you guys.
So if the bins don't have IDs, how do you calculate the number?
That's a different calculation. Because then, what happens, by picking 4 and 9, I get the distribution over bins which is 3, 4, and 3. But I could pick 4 and 8 and get the same distribution, 3, 3, and 4. If the bins don't matter, which one's first, which one's second, only the distribution over bins, 3, 4, 3 will be the same as 3, 3, 4, will be the same as 4, 3, 3. So then I have to divide by how many ways can I get the same distribution counts, right? That's a more complicated problem. Balls into bins refers to the fact where the first bin, second bin, third bin are different bins. We'll get there. Okay? So now we've done with the theory. We have a bunch of ways to count things. Pigeonhole principle counts min and max. What's the minimum amount of cars to transport 7 people if in each car I can only fit I don't know, 6 students? That's pigeonhole principle. Product rule, if I have 3 pants and 4 shirts, then and everybody goes to every pant goes to every shirt, then I have 3 times 4 ways to dress up. Sum rule, which I call partition rule, is if I'm counting a bunch of things, I can count them in this joint set separately. As long as the sets don't intersect, I can count in each set and then sum them up. Inclusion-exclusion principle, if the sets do intersect, then I have to take out those intersections. Combinations, numbers of ways to choose a subset of k out of n. Permutations, numbers of ways to permute k things or n things. R permutations, numbers of ways to choose a sequence of k, that is choosing k, but then permute them in every possible way. And balls into bins, which is effectively choosing the symbols of the separator between bins, which is k minus 1, out of that many symbols. Now, among all these ways to count things, when you hit a problem, you're going to have to figure out what's the problem asking for, which kind of counting strategy applies. A good idea is to use partition rule first if you can. If you can separate, I want to count how many people have diabetes in the world, but I'm going to count separately North America from Europe because there's no intersection. It's a good idea. And I count separately that, and then add them up. For example, I have an example here. I want to count passwords 6 to 10 characters. I don't know if we did this last time or not. At least, maybe you can tell me. 3 letters, at least 3 digits. Did we do this?
Yeah.
You did this example last time, exactly this one?
Something similar.
Something similar. Let's do this one really quick, just to recap what we're doing. The first thing, we use partition rule. Partition. To split the passwords into the passwords of 6, 7, 8, 9, and 10. Is that a partition? Passwords, are those sets disjoint? Passwords with 6 can intersect with passwords with 8? Or passwords with 7 intersect with password 9 or 10? Are disjoint or not? Disjoint. So disjoint means I can count them separately and add up the counts. Good. Now in passwords of 6, I have a bunch of possibilities. I can have 0 letters, 1 letter, 2 letters, 3 letters, 4 letters, 5 letters, or 6 letters. Right? When I have 6 symbols, here they are. Are those disjoint possibilities? Every password that has 2 letters can be the same as a password that has 3 letters or 5 letters? Can be or not? Are they disjoint possibilities? They are disjoint possibilities means I can just count separately.
Does it say at least 3 letters?
Yes.
So that's 3 letters.
At least 3 letters and at least 3 digits. That's the condition.
So should you not include 0 to 2 letters?
Right, I'm just saying that's all the possibilities of these passwords with 6 characters. Some of them are invalid. So which ones are the valid ones here? They have to have exactly 3 letters. Those are the only one that matter for me, right? Because in 6, to satisfy that condition, 3 and 3, I have to have exactly 3 letters. Everything else won't work. How about in the case of 8? If I have 8, I have 0 letters, 1 letter, 2 letters, 3 letters, 4 letters, 5 letters, 6, 7, 8 letters. What are the cases that are satisfying at least 3 letters and at least 3 digits? Some of those are invalid, but some are valid. Which ones are valid? Somebody else? Yes.
3, 4, and 5.
3, 4, and 5. Why 6 letters no good?
Because you need 3 digits.
So if I have 6 letters, I only have 2 digits left. So now I have more cases here that are valid for me. Now, how many passwords have exactly 3 letters within 8 characters? How do I compute this count? So this is all a partition mechanism to count things separately. And I don't care about those because all those are no good. No good, no good, no good, no good, no good, no good. But the ones that are good, I have to count, right? How many 8 sequences of 8 have exactly 3 letters?
Would it be 52, choose 3?
No. But it's close. You're combining 2 ideas. You have to do it separately. First of all, I have to choose the spots for the letters, right? They have to be 3 letters. In how many ways can I choose 3 spots, 3 locations for the letters or positions? 8 choose 3. So now I know this is a letter, letter, letter. This is a digit, 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 sorry. Digit, 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 right? So I choose 3 spots for letters and I have 5 spots for digits. But now in how many ways can I populate this with actual letters and digits? How many options I have for each letter spot? That's where your answer is close. For each letter spot, I have 52 choices. There's 26 small letters and 26 big letters. So any one of these spots will be a 52. How many spots I have with letters? 3. Are any combination possible? Any letter with any letter with any letter works? So it's what? Product group. 52 Choose 3, because I choose 3. How about the digits? How many possibilities for the digit spots, for each digit location are there? How many digits are I can put in a digit spot? 10. Is any possibility works with any possibility with any possibility? Yes. So how many choices? 10 to the what power is this one? So that's what we have here. That's mechanisms to count stuff. And we're going to need product rules, sum rule, partitions, combinations, all kinds of things. In these problems, you can leave the answers as a massive sum of stuff like that. You don't need to compute. Those numbers are big. You don't need to compute those, okay? We can leave the answers this way. But you have to sum it up with this, with this, with that, maybe with some other ones in here. It's going to be a big sum. So, the last thing I want to show you today, but we're going to finish maybe next time, Friday. What we did a little bit last time was to show that n plus 1 choose k is the same as n choose k plus n choose k minus 1. The reason this works is if I want to choose, so this is choosing k things out of n plus 1. This is choose k out of n, and this is choose k minus 1 out of n. We said why this works last time, which is I can pick one element. This is n plus 1 things. This is n, and this is the last column, n plus 1. I have to choose k out of n plus 1, and I have two options. Choose the last element. So if I choose the last element, it's this side. Plus k minus 1 out of remaining ones. This in here is choose, do not choose last one, choose all k out of remaining ones. So that allows us to build what's called Pascal triangle. For n equal 1, we get 1 choose 1, 1 choose 0, that's 1. And 1 choose 1, that's also 1. For n equal 2, we get 2 choose 0, that's 1. And 2 choose 1, that's 2. And 2 choose 2, that's 1. For n equal 3, we get 3 choose 0, that's 1. 3 choose 1, that's 3. 3 choose 2, that's 3. And 3 choose 3, that's 1. N equal 4. 4 choose 0 is 1. 4 choose 1 is 4. 4 choose 2 is what? How many ways I can pick 2 out of 4? 6. 4 choose 3 is the same as 4 choose 1. And 4 choose 4 is 1. What n equal 5? I'm going to have to expand on this other board here. 5 choose 0 is 1. 5 choose 1 is 5. 5 choose 2. What this Pascal triangle says, what this rule says, if you are here, 1 is 1, 5 is the 4 plus 1, that's that rule there. This 5 choose 2 is going to be 4 plus 6, right? 10. Because I'm applying that rule. 5 choose 2 is 4 choose 2 and 4 choose 1. That's n equal 5 and n equal 4 and k equal 2. How about this one here? 5 choose 3. This is a 4. Then 5 choose 4 is 5, and 5 choose 5 is 1. So you can see how this rule just keeps working like that. And there's no surprise, right? How many ways can I choose 0 elements? How many subsets have 0 elements out of 5? Which one? The empty set. How many ways can I choose 1 element out of 5? 5 ways, right? How many ways I can choose pairs? AB, AC, AD, AE, BC, BD, BE, DC, DE, 10 pairs, right? So Pascal triangle works by saying this is the same as that. This one here is the sum of these two. This one here is the sum of these two. That's the sum of these two here. This one here, for example, is that. This is the sum of these two. This is the sum of these two. This is the sum of these two, and so on and so forth. That gives me a very efficient way to compute those, which are called binomial coefficients. The reason they call that, because people have looked at the following polynomial expansion. What happens if I do x plus y at n? Remember when I did p minus 1 times q minus 1 times r minus 1, an hour ago? I do that expansion. What am I going to get here? Suppose this is 3. This is x plus y times x plus y times x plus y. How many terms I'm going to get when I expand everything? 8 terms, 2 to the 3 terms. All terms have degree 3. No matter how do you expand those in terms of a polynomial, you're going to get things like x cubed, right? Because x times x times x. I'm going to get a bunch of x squared y, a bunch of x y squared, and a bunch of y cubes. Everywhere you expand x times y times x, you have to get something from each parenthesis. So the total degree is 3 factors. Number of factors. But those 3 are some x's and some y's. So how many ways are there when you make these products? There's 8 total terms. How many of those 8s are x cubed? In how many ways can I get x cubed? What way is that? Which is x times x times x. So that's one way. That is 3 choose 0. How many ways can I get x squared y? What are those ways? This x times this y. Right? X times y. What? It's another one. X times y times x. That gives also x squared y. And then y times x also gives x squared y. So how many ways can I get this? 3 choose 1. This is 3 choose 2. And this is 3 choose 3. These are totally in here 8 terms, but I group them by the polynomial form. I group all s squared y together, all x y squared together. What happens if I have x plus y to the 4th? How many ways to get x to the 4th? one way, right? X times X times X times X, which is 4 choose 0. 4 choose 0 is 1. How many ways to get x 3y? There's 4 choose 1 way. How many ways to get x squared times y squared? 6. That's 4 choose 2. The reason there's 6 ways to get x squared, y squared is that look at those parentheses. I'm always going to have 4 factors, right? Someone from here, times someone from here, times someone from here, times someone from here. How do I get 2 x's and 2 y's? I have to pick which parentheses I choose the x and which parentheses I choose the y's. I have 4 total factors. Which ones of them are the x's, 2 x's, and which ones of them are 2 y's correspond to choosing 2 out of 4. So that's why I get 2 out of 4 here. I get 4 out of 4 choose 3 x y cubed, and I get 4 choose 4 x 0 y 4, which is only y 4. This works in general, of course, and I can also prove it later on in this term by induction. I can say, using this formula here, if x plus y to the cube was this, multiplying with another x plus y, how do I get x3y? I can get x3y by either getting x squared y multiplied with what do I need to get x cubed y? With an x. So I either get this one multiplied with x, but I can also get x cubed y from x cubed multiplied with an y. So this coefficient 4 choose 1 comes from all these guys, 3 choose 1, when I multiply it, I have a new factor here, multiply with an x, or from these guys, multiply with an y. So that's why this coefficient here is the sum of these two, which is this formula. So in general case, what do we have? Is n choose 0 times x to the n y 0 plus n choose 1 x to n minus 1 y1 plus n choose 2 x to x n minus 2 y2 plus n choose n minus 2 x2 y n minus 2. That's the tail, n minus 1 x y n minus 1 plus n choose n x 0. That's good for any xy real numbers. Because the expansion is mechanic, it works no matter what values we plug in for x and y. So for example, if x equal 1 and y equal 1, what would we get? We get n choose 0 plus n choose 1. Every xy is 1. The sum of all of these is 1 plus 1 is 2 to the n. This is easy. We could have proven in other ways. We could have looked at this and say, this is a number of subsets with 0 elements, number of subsets with 1 element, number of subsets with 2 elements, all the way to number of subsets with L element, which is the whole set. So what is this? This is the number of all subsets with 0 plus all subsets with 1. This is all subsets. But how many subsets are there all the way total? 2 to the n, right? If A has n element. Now, one more thing that's not so easy to prove, but I could get it from that formula. What if I put x equal 1 and y equal minus 1? What is this formula becomes? How much is 1 plus minus 1 at n? 0. And what do I get for the expansion? N choose 0, but then the sign changes, right? This is minus n choose 1 plus n choose 2, because the minus 1 would cause to alternate sign. Now I can plug in anything I want for this x and y. I just showed you example 1 and 1, 1 and minus 1. But I could plug any values I want in there. It's called a binomial expansion. So quiz tomorrow. We populated the website with all kinds of interesting things, like midterm practice from last year's, and solutions for the previous recitation. Sorry. We'll have to do the recitations. We'll go over Wednesday and Thursday. Yeah.
We gotta make our own. I literally forgot what we were at school last night.
Let me shut up. I'll do the recitations. I forgot. I didn't know.